So I want to discuss an interesting property of A cross B with you. I'm not going to tell you what it is. I'm just going to do some algebra, and we'll see what happens, all right? So here we go. You ready? So I'm going to start with the following. A cross B has a norm. I'm going to square that norm. Okay? I can tell you this much. What I'm interested in is this. My goal is to sort of learn something about what the norm of A cross B is. The norm of A cross B is a scalar, right? It's the length of this cross product vector. And I'm interested in what the length of that cross product vector is going to be. And I'm starting with this. Okay, so let's just recall for a minute, just so we remember. A cross B equals the vector A2B3 minus A3B2, comma, A3B1 minus A1B3, comma, and then A1B2 minus A2B1. Okay. So the norm of this squared would be the sum of the squares of all these components. So you would get this. A2B3 minus A3B2 squared. And you can start to see, wow, this is going to be some kind of horrible algebra nightmare. And I'm going to spare you a lot of it. So, and actually, I'll have a little challenge for you, for those of you who are interested. Okay? So here you go. All right? Now that would have to square out. Okay, and if you do, I'm going to do the first step in squaring this. And then you're going to see it's pretty scary to look at, and then I'm going to rewrite it in a new way, and things will get much nicer. Okay, so what you have here is this. Like if we square that first thing, you're going to get A2 squared B3 squared minus 2A squared B3. I'm sorry, not A squared. A2 B3 A3 B2 plus A3 squared B2 squared. Okay, so we'll just let the algebra nightmare continue for a little bit longer, and then I'll save you. All right, so the next term, A3 squared B1 squared minus 2A1 A3 B1 B3 plus A1 squared B3, oops, my mistake, B3 squared. All right, and then one more line of this, plus A1 squared B2 squared minus 2A1 A2 B1 B2 plus A2 squared B1 squared. Okay. Now, here's where I'm going to just do something magical. I am going to tell you that that horrible-looking expression is the same as this. A1 squared plus A2 squared plus A3 squared times B1 squared plus B2 squared plus B3 squared minus this. A1 B1 plus A2 B2 plus A3 B3 quantity squared. Okay, now I've skipped the reasons why we get this expression, and I leave that to you. So something that if you'd want to, if you're interested, try and figure that out. So why did I do that? Why did I spare all this algebra? Because if we look carefully at what we have here, it's actually recognizable. If you look at just this piece for a minute, it looks like we were trying to take the norm of vector A, except one thing's missing. Normally we take the square root, right? The norm of a vector is the sum of the squares of the components, and then we take the square root of that quantity. So this, really, another name for this could be norm A squared. That's what that really is. Okay? And then in the same way, same reasoning would tell you that that's the norm of B squared. Okay, so far so good. We have norm A squared, norm B squared. Well, that's a lot more compact way to write things. And when you look at this expression, you don't quite luck out that way, right? You look at it, you say, hey, wait a minute, that's not like in the earlier case, this was a1 squared. But what do you have here? You have the first component of one vector times the first component of another vector, plus the second component of one vector times the second component of a second vector, right? Plus product of the third components. That's a dot product. That's what that is. So this is really minus a dot b squared. Okay, so that was the goal, given all that algebra, what we could do. Now, just a few more simple steps and things get very nice. We have a definition for dot product that we can apply. So we can say norm A, norm B, cosine theta, quantity squared, like that. Okay, now I'm happy because I could see some common factors, right? If we notice, right, we can take out this. That's the common factor right there because it's over here too. So what do we get? We get the norm of A squared, norm of B squared, times 1 minus cosine squared theta. But that's really the norm of A squared, the norm of B squared, times sine squared of theta. So altogether, what does this imply? It implies that the following. Don't forget, this expression up here equaled A cross B norm squared. That's how we started this whole story. And my goal is to figure out something about the norm of A cross B. And we've done it. The norm of A cross B must equal norm A, norm B, sine of theta. So this is the interesting little property. All right. So there's two things I want to discuss now about this special property. One, it actually becomes a way to check for some things. So for example, if A cross B equals 0. Now I better be careful when I say that. If I say A cross B equals 0, this thing is what's called this is called the zero vector. Okay? That's what that thing is. That's the zero vector. What would that tell us? Well, if that were the case, then we would know that the norm of A, the norm of B, times the sine of theta equals 0. Okay. Now, why is that? Because if we take the norm of the zero vector, we get 0. Okay. So really, in some books, this 0 looks like very bold to sort of indicate that that's not the number 0, but that's the vector 0. Zero vectors is a vector with all zeros in its component. So if for some reason that happens, then what do we know? That means that this is the case, right? That means that this is the case. A cross B equals 0. All right, the norm of it. Now that's normal number 0. But that implies this. Well, what do we know? We know that the norm of A can't be 0. We know that the norm of B can't be 0 because we're not going to do any cross products with zero vectors. These are non-zero vectors. So that implies that the sine of theta is equal to the number 0. So then theta must be 0 or pi radians. So the angle between the vectors is 0, or the angle between the vectors is pi, or 180 degrees. So what does that tell us? It tells us that the vectors that we started with, okay, fine. This implies that vector A and vector B are what we say parallel. Okay, so it's sort of a strange thing. They're parallel. There's sort of a linear algebra way to look at that. If two vectors are parallel, I mean, if I say a vector A is parallel to a vector B, then you should ask yourself what that implies about the relationship between vector A and vector B. It means that, really, the vectors are a scalar multiple of each other. Right? Okay, so like if you have a vector A over here somewhere in space, and I tell you I have a vector parallel to that, maybe like this, vector B, then there has to be some scalar number k that I can multiply B by to get A. Right? If for some reason the third vector I'm thinking about, say I have a vector like this going like that, maybe much longer, I call that vector C, then the same is true. Vector A must be some number, some scalar k times C, Right, let's be clear that these things that's a scalar, and that's a scalar. All right. In this case, what do you know? K must have been less than 0 because the vector C is pointing the exact opposite direction. Okay. Over here, K must have been greater than 0. Either way, that's the case. All right. So A equals K times B. All right. So if we think about our determinant then, our determinant definition, what do we know? A cross B, since the vectors are parallel, you're going to have A cross K times A, right? And our definition is going to look like this, I, J, K, or determinant, I should say. The components of A are A1, A2, A3. The components of B, which is really K times A, is KA1, KA2, and KA3. Now, for those of you who know something about determinants and linear algebra, okay, this is an example where these two vectors, this vector here and this vector here, are sometimes we say they're linearly dependent. Okay, one vector is a multiple of the other. Okay, there's other ways things can be linearly dependent, but that's what we're talking about here. When that's the case, the determinant always comes back as 0. So you should know that. All right, but watch what happens if you just do the math here. You'll start to see it. So I times its minor would be A2, A3, KA2, KA3, minus J times its minor, plus K times its minor. So I won't do all of this, but you can see, watch what happens in the first spot. I times, you're going to have K, A2, A3, minus K, right, A3, A2. Well, that whole thing is just going to equal 0. And the reason that's the case is because if you look at these little pieces here, A2, A3 are the same, A2, A3 are the same. They're just both getting multiplied by these K's. All right? So you can see the first component of our cross product vector is going to be 0. Then the next component is going to be 0 for the same reason, and so on. So that's sort of how determinants confirm that this can happen. So what we know now is we have a way to check if vectors are parallel, right? We could check the cross product, and if the norm of the cross product is 0, then the vectors must be parallel, right? That's sort of a nice thing. Okay, what else can we say? Well, we can also talk about just geometrically. Now, we have this property now, you know, that the norm of A cross B is equal to the norm of A, the norm of B, and times the sine of theta. And my claim is that you've seen something like this before a long time ago. So I'm going to draw a picture, and this will become pretty clear. So say I have a vector A going this way, and a vector B going that way. All right, what do we know? Well, we know that this entire distance has length norm B, and that entire distance, oops, hold on a second there, has length norm A. And what I'm going to do is I'm actually going to make a parallelogram out of this, as if we were going to add these vectors. Okay, so there we go. There we go. Okay. And you learned a long time ago how to find the area of a parallelogram, right? What did you learn? You learned that the area is equal to the base times the height. Well, the base of our parallelogram, I'm going to let it be norm B, so it's going to be norm B, like that. Okay? And I just need the height. Well, the height is going to be this perpendicular distance right there. Okay? Now, I could have drawn it anywhere. I should be clear. I could have put the height over here or over here. I put it in this location because I wanted to be able to see a nice right triangle here. And here's what I like about that little green right triangle. I know how long the hypotenuse is. The hypotenuse has length norm A. Right? So we can actually solve for the height. Here's why. The angle between the vectors we call theta. And we can do that. We know we can find that if we have two vectors. So what can we say here? We can say that the sine of theta is equal to the opposite, which is the height I want, over the hypotenuse, which is the norm of A, which I know, which I have, right? So what does that give us? That gives us that the height is equal to the norm of A times the sine of theta. Well, there you go. You put that in here, you get norm A sine of theta. And what we've just shown is that the area of the parallelogram spanned by vectors A and B is the norm of the cross product of A and B. I've left an O out of there. Okay? So there you go.